Today we'll speak about Tecplot feature that is the CFD analyzer that allows you to gain insight within your CFD data. My name is Analyser and I'm working at Genias Graphics. For today's summary, a brief word about Genias Graphics for you to know who we are and what do we do basically. I'll speak then about how to set up the Tecplot environment so Tecplot can know what variables are to be used within the CFD analyzer. We'll also see in that occasion how to visualize your boundary conditions and your field variables, how to set them. We'll see then how to calculate a bunch of new variables that are already within Tecplot, so you can calculate them automatically. We'll then present how to perform an integration, and there is actually various type of integration you can perform within Tecplot 360. We'll see how to calculate turbulence functions and how to calculate particle paths and streaklines. We'll then see how to extract flow features such as shock surfaces or vortex curves, for example, or separation and attachment lines. And we'll end up with very little tool that allows you to analyze your solution errors. So Genias Graphics, we are providing solutions to visualize and analyze scientific data. We are Tecplot exclusive distributor within Europe and Western Asia, and we have approximately 1,300 organizations that are using Tecplot. We have more than 20 years of experience, and we are based in Regensburg in Germany, so it's southeast between München and Nuremberg. We do training, consulting, as well as software development. And our largest customers are mainly from the aerospace domains, such as Airbus, Dassault Aviation, DLR, NVDA, but also marine for marine applications, or LTU, Unera, or Siemens power generation. First of all, how to set up fluid properties, boundary conditions, and field variables within Tecplot. The recent thing you should know is that Tecplot works without dimensions, so all of your units must be consistent. Namely, if you're expressing your length in, for example, in meter, and your time in seconds, your velocity should be in meter per second, or your volume in cubic meter. The fluid properties dialog allows you to describe the fluid model you used to create your dataset from within your solver. And you can set and visualize the boundary condition in the geometry and boundaries dialog. Field variables enable to automatically compute a set of predefined variables, so you need basically to tell Tecplot what variable it should use for the convection vector and state variables. All of the settings can be saved or loaded, and if you're using a particular data loader, basically Tecplot sets that up automatically for you. So I'll start Tecplot 360X 2016 R1, which is the latest release. And I'll just load a little layout here. So basically, it's a very simple data set. Here we just have a slice and few stream traces. And this is a transient case which was computed within Fluent. As you can see, it's a fluid structure interaction. So if I play the movie here, the little elastic flap here is moving. Okay. So the CFD analyzer can be accessed within that Analyse menu. And the first thing you can do is to set up your fluid properties, So here, for example, we have an incompressible flow, and we'll specify a density of 1.225, which is the density of air at approximately 15 degrees. We won't be using any heat-related computation in that case, but we will want, for example, to set up the viscosity and use a field variable that you can select right here. If you have a compressible flow, you can set up a gas constant or and the gamma, which is the ratio of specific heat sets, pressure, and volume constant. Okay. Then you can set up a bunch of reference values that allows you to normalize new variable when you compute them. Third thing is that you can set up field variables, so Tecplot knows what variables are to be used to define the convective vector. So here we'll use velocity and use x, y, and z velocity. And you need two states variable. Here we won't use the density as it is constant over time and in the whole domain. So we can verify that at any moment in the dataset info. So here if you choose the density variable, as you can see for every zone it's 1.225. Regarding geometries and boundaries, so it's automatically recognized in Tecplot for some data loaders such as Fluent. However, you can define them yourself by so you basically choose the boundary condition you wish to use, and then you can select a bunch of zones, and you can just specify, for example, a plane within that zone, and even a subset of that plane. You can display those boundaries to make sure they are well set. So here, for example, I've got the velocity inlet in green, pressure outlet in blue, and I've got walls in red there. Okay. So once you've done that, of course, you can save those settings and load those settings at any time later on. And basically, Tecplot has everything it needs to be able to compute new variables, for example, within the CFD analyzer. And that's my second slide here. So how to automatically calculate variable. So all of those variables are derived from Matplotlib3D and its successor FAST programs. It includes grid quality analysis variables, as well as field scalar variables and, for example, vector flow variables. You can calculate a variable on demand when working with big data sets that allows you to compute that variable only for the elements you are needing for further computation or to visualize. You can also choose the location to store the new variable, so namely cell-centered or on the nodes. So we'll see a brief example here. So once again, in that Analyze menu, you have that Calculate Variable dialog. And here you can choose all of your variables. So here, for example, those variables are related to the mesh. So for example, the Jacobian. And then you have field scalar variables. And in the end, you have vectors or even tensors. A quick way to actually find the variable you wish to use is to hit the first letter. So here I'm hitting V to get velocity, velocity, and so on. And let's say we want to compute the velocity magnitude, so you can just choose it here. You can normalize that variable either to its maximum magnitude or to the reference value you could have previously set. And you can choose, as said, the new variable location, so either on the node or on the cell center. I will toggle off calculate on demand here, as my dataset is not that big, so I can compute it for the whole dataset. So here it is, and I have a little dialog that tells me where is the minimum and maximum value and which node it is located. Okay, calculation was successful, so now if I go on my variable list here, for example, I have a velocity magnitude variable. So here I have an ISO surface, I turn it off. And here we are visualizing the velocity magnitude within our domain. So every time you compute a new variable, it appears at the end of your variable list. Okay. So now we'll speak about how to perform an integration within Tecplot, sorry. So you have numerous scalar or vector integrations that are available, and you can integrate over zone or time strand. So basically a time strand is a group of zones that correspond to one object, and that object can exist in many time steps, for example. You have the possibility to limit the integration domain to a subset of a zone. So if you want to integrate over within a range of indexes, for example, you can. The result, you can display it as text on your frame or save it in a text file, but you can also visualize it and plot it as a XY line plot. So once again, in the Analyze menu, you have that Perform Integration tool. And here you have the type of integrations that are available. So here, for example, we will derive forces and moment on the elastic flap that is here. And you can set the origin for the moment calculation. We'll integrate over time strand. So basically here I have one zone per time step that correspond to my flap here. So I will just select it as my time strand number 4, which is called wall. and this is the flap. You can show those results as text, but you can also plot them. So by hitting integrate, Tecplot performs integration over time, and here you have the results of your integration. So for each time step, you have the lift, drag, sides, the moments, and the forces that are basically lift, drag, and side. And you can save that as a text file, for example. So you can just click Save button. You can make it a text as well, so you have that text that is available here on your frame. Here it's big, so I will just delete it. Regarding the plotting here, so let me just tie my frames. Here I have my 2 frames, one over the other. So this is a XY line plot, and you can access all of the results of your integration. So we'll just copy that lift, and I'll call it drag and side. So we'll basically have all of our result on one plate. So you can change the symbols as well. So let's say here we want little deltas, for example, and we wish to have other outline colors. So let's say green and blue. And same here, you can fill it, for example, by a specific color. So let's choose again green and blue. So by clicking Ctrl F, you can fit basically your result here. So I will just change a few things here. Once again, having a green and blue lines, it allows you to better visualize your results. And here the drag and side are quite high regarding the lift, so I just put them on another axis here. So by hitting Ctrl F once again, we have all of our results within one frame. I will just display a line legend so we can see what line corresponds to which result. So here we have our 3 components of forces, and if we play the movie in the top frame, as you can see here, you have a time slider that basically tells you at what solution time you are currently looking, and you have the results that are displayed here. Okay, so this is it for basic integration. If you wish to integrate on, let's say, a slice or something, you will need to have it as either a zone or a time strand. So, for example, here I will position a slice on my x-axis. For example, it did before the flap here. And if I want to integrate something on that slice, I will need to write it as a zone. So you can extract slices over time, but also isosurfaces, geometries, or stream traces. So you can perform integration on those features, let's say. So here it is, I just extracted it. So now I have a new zone that is my slice. So I can display it without mesh up. And as you can see, if I don't display my slice, it's actually a zone. So I will see it anyway. Now you can perform an integration. So let's say, for example, you wish to get the mass flow rate through that slice. So once again, through time strand. So basically here I have one zone per time step that is my slice, and they're all in the same time strand, so consider that the same object. So here is my slice, and here is the list of zones. I'll show the result, let's say mass flow rate, MFR. I won't show tabulated results, and here it is. So now I have the mass flow rate along time, a bit like the integration for the forces and moments. In XY line plot, you can at any time just click a zone and or line, and you can just perform a Fourier transform within one click. So here you have the frequency response. Let's just show bars. So you have the frequency response of your mass flow rate through the slice. Okay, so this is it for the basic type of integration. You can play a bit with it and contact us if you have any question regarding that. There is quite a bunch of possibilities, and we won't be able to show anything, of course. So now I'll speak about how to compute turbulence functions. So basically, if you have two of the following variables, you can compute any of the 3 others. So if you have a K epsilon model, for example, you can retrieve the turbulent frequency or viscosities. So to do so, you just go to So analyze once again and calculate turbulence functions. And here we have computed the kinetic energy and dissipation rate. So this is something Tecplot automatically recognizes if you're using, for example, a Fluent dataset. But if you are having your own convention for your variable names, you need to basically select those variables here. And then you can compute any of the three others. So for example, the turbulent frequency. Once again, you can choose whether you want to store it on the nodes or within the cell centers. And here I once again took it off that calculate and demand. So by hitting calculate, I have once again a little information for the extremas, the minimum and max values, and a little information that tells me that the calculation was a success. So let me just display another slice here, one way, for example. And now we can plot, so we have once again a new variable that is the turbulent frequency, and we can plot it here. So it's quite straightforward actually to get new variables within Tecplot, especially for those variables that are already defined. Now I'll speak about particle path and Streaklines. So basically, what is the difference with stream traces as well? Stream traces is basically a visualization mean of the velocity field at a given instant. So every time you move to a new time step, your stream traces will get updated to fit the new velocity field vector, basically. A particle path takes that into account, and it's actually the path of a particle, a real particle would travel through your volume. A streakline is basically a set of particle paths in which you release a new particle every time step, for example. And the analogy is like you release a thin stream of smoke at every time step, for example. You can animate streaklines, for example, to your screen or to a file. So let's see that. So you can right-click stream traces to extract them, delete or delete them all. That's what I'm doing here. And I will just display slides to be able to see my stream traces in a, well, let's say I want the second one here, so I just delete the first one. Here is the stream traces. So as you can see, every time step I am moving, the stream traces gets updated regarding the instant velocity field. So you can animate stream traces in that detail dialog here. So in timing, you will need to show markers. So for example, having markers colored by pressure. And in animate here, so just add a few steps so you can animate it on screen. And you would see the stream traces markers getting animated. You can have time concurrently, of course. And the distance between two markers here is proportional to your velocity field. Okay. So now let's say we are interested in a particle, the real path, let's say, of a particle through our volume. So you can use it here, calculate particle path and streaklines. So here we'll use a particle path. You can define mass and particle options. So, sorry. For example, you can define the orientation and the intensity of your gravity. And you can give a initial velocity, so either the local flow velocity or zero, or a specified velocity. Should you wish, you can calculate particle width temperature, so specifying a termination temperature and a time constant. You can specify either general coefficient, or such as the ballistic one actually, or recompute it by using drag coefficient or by calculating it from the mass and the radius of your particle. So we will not use that here. You can create also a single order zone from your particle path that allows you to animate them, for example. So I'll just click calculate here. Here it is. And now I have a particle path that has been calculated as along my streamline here. So I'll just turn on mesh so we can see actually the path. And I will just color, let's say, the mesh in red. And if you wish to see, the points, here is actually, you have 1 point per integration time step. So there is an important thing here is that your integration time step must be equal or under half of your delta time between two solution types. And here is my particle path, so that the real path a particle would travel through your volume. So you can delete them all just by hitting delete here. And now we'll see a Streakline. So a Streakline is basically a particle path, but you release one new particle every second, or every solution time here, for example. So I just calculated, and you can also animate them on screen. So I just click animate here, and as you can see, you see it getting updated. You can animate it on screen or export it to a file. Oh, sorry. The include zone animation here allows you to have your time updated at the same time. So you would see here, for example, if I play it without toggling that on, as you can see, the flap stays still, and it gets updated if I toggle that on. So, sorry. So now we'll speak about extracting flow features. So the algorithms are based on the FX library that was developed by MIT. And you have the possibility to extract vortex cores or shock surfaces, or also separation and attachment lines. So all of those commands can be recorded in a macro, and we will have a webinar next week about how to script macros within Tecplot to automate your workflow. So once again, it's quite easy. Just for you to know here, we have a little vortex. So a quick way of seeing it would be, for example, to feed stream traces around, or even as a rake. Of course, it takes a bit of time. So as you can see, we have something like a vortex here. If you want to identify it really easily, so I just delete my stream traces, you can go to the Analyse extract flow feature, and here you can have, for example, the vortex cores. So we'll use the velocity gradient eigenmodes of the eigenmodes of the velocity gradient, and we'll just click extract here. So here I have a new zone. I'll just turn off scatter and make it a bit more visible. So, for example, once again using a red mesh and maybe a bit thicker. So here is my vortex core, and you can actually see it quite easily. Okay. A very last feature, but the possibility to analyze solution error within three mesh or between three meshes. So basically you will need to get three meshes that are coarse, medium, and fine, let's say. And every time you refine a mesh, you need to add a point on each segment. So if you have a coarse mesh with n cells, a medium mesh would have 4n, and a fine mesh 16n cells in 2D, or 8n cells and 64n cells in 3D. The accuracy is estimated using a Richardson extrapolation, and you can plot the one norm and infinity norm or max norm, as well as the accuracy on each node. You can also extrapolate the result on your coarse mesh to basically see what are the difference with the original solution and the extrapolated fine one on the coarse. So I prepared a little layout for that. So it's very simple example. I'll just find it here. Okay. So yeah, I'll just turn off contours. And just for you to know what we are speaking about here. So we have three zones. Those are rectangular zones, and the first one is made of 4 cells. The second one is made of 16 cells. So basically in the middle of each segment you add a point, and so on for the fine one, which has 64 cells here. So there is pressure that has been calculated on those cells. So here is for the coarse one. The medium one has such a contour, and the fine one has this contour here. So we'd like to know what is the influence of the mesh regarding those solutions and how to compare them. So in the Analyze Error dialog here, you can first of all select the zones that are corresponding to your 3 meshes, and then you can enter the theoretical maximum accuracy of your solver. And then we will use that pressure variable, which is the one we are interested in. That's the contour here. And you can choose to plot the accuracy on all grid nodes and plot the overall accuracy. So that's a logarithmic scale. So you have the one norm and max norms that are average here. And by clicking OK, you just get the corresponding plot. So here actually you have the spacing, which is basically a relative scale. So spacing of 1 would be that green segment here, a half would be the red one here, and a fourth would be the black one here. And you have the one norm and max norms there. So as you can see, as there is a difference in slopes here, it may indicate actually discontinuities between your results. So deleting that frame, here we have 2 frames created, and the second one is the accuracy on the coarse mesh. So you can just display the mesh here, and we will just get interested in the in labeling the points actually with the accuracy. So as you can see here, we have maximum accuracy, which is 2 on the sides, and we have 1 on the vertical bar in the middle and the horizontal 1 at the top. So it allows you to plot where your solution is accurate or not. One last thing is that you can extrapolate solution. So, well, actually it doesn't matter. By clicking that, you would say OK, and now we have 2 new zones that are created. So you have an estimated error on the coarse mesh. So once again, I will just label points and cells so we can see. So here is basically the estimated error per node. And the other thing is that you have an extrapolated solution on your coarse mesh. So you can compare your coarse mesh with the estimated solution quite easily. Okay, so this is it for the Analyser. And I will just show you a very last slide. So where can you get support for Tecplot or raise your questions? So of course, question will be answered today, but you can basically email us at any time at support@tecplot.de, or if it's urgent, you can just call us, which is the easiest way for us to answer you in a timely manner. You can try Tecplot for free at www.tecplot.com. And I would like to get your attention about our new certification program. It takes basically 1 hour, and you would get all the information you need to perform basic visualization and post-processing within Tecplot. You'll get a written certificate for your records at the end of the certification. So thank you very much. Please don't hesitate to contact me for any information you may need. So my email is there, antoine.lager@geniasgraphics.de, and we'll remain online to answer the few questions that are popping out. Thank you.